Greetings everyone. Welcome back to Multivariable Calculus. Now let's use some of our partial derivatives to do a measurement on some 3D functions, some 3D graphs of multivariable functions, I should say. Tangent planes and normal lines. The idea here is just an extension of a tangent line that you would have normally done in Calculus 1, Calculus 2, and a little bit in this course at the beginning as well. Before in calculus, you would have had a curve, so you would have a line tangent to the curve at some point. Now that we're dealing with surfaces when we graph our two variable into z functions, then what we can generalize the tangent line into being a tangent plane. And there are a few applications of these tangent planes, just like tangent lines have applications to curves. If you remember, tangent lines are useful for approximating the values of curves. They're also useful for approximating a shape of a curve, and so on and so on. Tangent planes are very much the same. You can use a tangent plane as a really close local approximation to a piece of a surface, and you can even use it to put if you put enough of these small planes together, you can approximate shapes of surfaces and things like that. But here our goal is just to talk about how we can locate and create equations of tangent planes, and normal lines, right? Normal lines is something we didn't do with curves very much because we only really needed the tangents to our curves. But we are going to start needing normal pieces to those, especially if you start doing applications in chemistry and physics. You'll need a normal vector, a normal line, something that's perpendicular at a point is really what those are. So, all right, let's begin. Remember from the last few sections, we've talked about the gradient, directional derivatives, gradient. And remember, the gradient was said to be a vector of coming from your function. And if you were to pick a level curve or surface, in other words, letting your output be a certain value and getting the curve or surface that is the result of that, then the gradient at the point where you created the level curve or surface, the gradient at that point is always perpendicular to that level curve or surface at that particular point of creation. Okay? So the level surfaces can give us an insight into different levels of the thing that we're graphing. But here we're going to go a different direction so that we can use this perpendicularity, orthogonality, to our advantage. Okay? So if you have some function, z equals f of xy, right? Those are the functions that we typically study a lot in these multivariable calculus things that we do. Okay? What you can do is subtract the z over to this side, and you'll get 0 equals f of xy minus z. Now, what you can do is think of that as one level surface of a higher order function, a function that has a w equal to some function of x, y, and z. But the particular function of x, y, and z that we're referring to is f of xy minus z. Okay? So imagine there was some function w that was equal to that. Then 0 equals f of xy minus z is just one level surface out of this bigger function. What does that mean? Well, remember, gradient at a particular point is always perpendicular to its own level surface, right? So if you take the gradient of this w function and evaluate it at the point where you're interested in finding this, whatever point you're interested in measuring on your original function, you'll have an x, y, and a z value, so you'll get a point P from that. Okay, so if you take the gradient of w, the bigger function, and evaluate it at point P, then that vector that you get from this gradient will be perpendicular to your original surface, because our original surface is the level surface of W, and it's going to be at the point P because you're getting the coordinates of P originally from the function. So point P exists on your function, therefore the gradient of W at point P is going to be corresponding to its own level surface, which is your original function, and therefore be perpendicular to it at the point P. It'll be perpendicular to your function at point P. So in other words, you have your surface. We're saying that this one surface that we're measuring, that we're looking at this function, could also be, or is also, a level surface of some other higher level function. We don't care too much about the higher level function. We're really just interested in this one surface. Okay? But the fact that it is linked to that higher level surface, I can take the gradient of that higher level surface, and it will give me something that has a vector that is perpendicular to my surface. Okay? So the result from that is, if I take the gradient of W, remember W is just f of xy minus z. So the gradient is just the partial of f with respect to x, the partial of f with respect to y, and then the partial of the whole thing with respect to z is just the derivative of the negative z portion. So you just get -1. Okay? Well, that means that is the calculation of a normal vector to our surface at the point we're interested in, which is going to be some x and some y that we're going to pick, and then you would plug it into the function and get the z coordinate, so that'll be the point P that we were talking about over here. Okay? So, if this is a normal vector to my surface, right, I've got my surface, I've got some point, I've got the normal vector to my surface now, well, that's all you need to create a plane and a line. I just need a vector and a point, and I can use those to either create a plane or a line. Specifically in this particular aspect, if this is a normal vector to the surface, then that means it would also be normal, it would be perpendicular to the tangent plane. So what do? I use the components of that vector as my coefficients for the equation of a plane. Remember, a, x minus x naught, b, y minus y naught, c, z minus z naught equals 0. That thing. My a, b, and c, though, are the components here. The partial with respect to x, the partial with respect to y, and -1. So that's this, and -1 right here. And then, of course, the point that we're interested in will be a, b, and the function evaluated at a, b will give me the z value of the point. So x minus a, y minus b, z minus f of ab. That's the equation of a plane, right? Okay. Also, a normal line. Remember, all that is something where I have a point and a vector, and that's all I need to create a line. I just say the point plus the vector times t, and I'll get a line in the direction of that vector going through that particular point. So that's all we're doing here. Look, I have x component of the vector times t plus the x component of the point, right? For my x, these are parametric equations, don't forget, that's how you can make a line, right? The y, I have vector component t plus point component, vector component times t plus point component. I have all the x, y, and z parametric equations in there. This would then create a line that is normal to your surface. Okay? So, these are the things that we'll be using to compute in the examples here. I'll be using the formula for a tangent plane. Really what I'm going to do is I'm going to compute the normal vector, and then we're just going to use it to create a plane the same way we always create planes, and create a line the same way we always create lines. these are just your formula setups if you like to memorize formulas. So now you must be screaming, put your money where your mouth is. Put your math where your mouth is. Fine. Let's get some examples of finding some tangent planes and normal lines. Okay? So, function of xy, f of xy, is 5x plus 3y over x squared plus y squared plus 1. And then we're interested in the domain point 1, 2. Okay, so remember what that means is my x is 1, my y is 2 for this example, but I've got the whole surface and my xy plane has that point. So if I'm looking down at my surface over that point or under, depending on where your surface is on the thing, right? I'm going to be looking for the tangent plane corresponding to the output that point gives. So it's going to be something either above or below, right? The xy plane. But this is the domain point, okay? Well, I've got to do my partial derivatives first so that I can have my gradient and then I can turn that into a normal vector. So I'm going to start with my partial derivatives. Partial with respect to x, f sub x, is going to be a quotient rule. So I've got low d high, in this case, is just 5, minus high, and then d low is going to be the derivative of this, but remember we're just doing with respect to x, so it's just going to be times 2x, and then over the square of what's below, like so. So let's see, my partial derivative can reduce. I'm going to have 5x squared here minus 10x squared here. So I've got negative 5x squared. Next, I've got, let's see, 6xy, and I've got 5y squared and 5. So that's really all I've got. Plus 5y squared plus 5, and then minus 6xy. Yeah. All right. And then, of course, I'll leave the bottom alone. X squared plus y squared plus 1 squared. Yum, yum. Okay, so f sub y, my partial derivative with respect to y, is going to be very similar, right? It's going to be my x squared plus y squared plus 1 times 3, though, when I do the derivative of the high part, because I'm just doing the derivative with respect to y, the x portion goes away to 0, minus the high part times the d low part. In this case, we'll get 2y. And the same denominator, right? Square of what's below. All right. So all together, I'm going to have 3x squared. I'm going to have 3y squared, but I'm going to have minus 6y squared right here. So negative 3y squared total. Then I still have my plus 3. And I've got my minus 10 xy. Alrighty. X squared, y squared, 1 all squared. Okay, so I've got my partial derivatives here. I'm going to be interested in the function value at 1, 2, because I've got to have my z value to make the line and the plane. Okay, so from here, I would do f of 1, 2, right? F of 1, 2 is just going to be 5 plus 6 is 11 in the top. And then 1 plus 4 plus 1, 6 in the bottom. Okay, so I've got my z value now. The location on the surface where this point actually resides, right? So that's the point that I'm making the tangent plane to. I've got my partial derivatives so that I can set up my normal vector at the point 1, 2. Okay, so let's go ahead and compute those as well. Let's see if I have space right here. F sub x at 1, 2, right? So let's go ahead and crunch those up. I'm going to have -5. I wonder if it would be easier from here. It may almost be easier from there, huh? To have all of the pieces to compute. Would it? I'm just going to go with it. Okay, so I'm going to have -5 plus 20, right? So that's 15. Well, plus 5 is back to 20 again. And then -6 times 1 times 2. So -12. 20 minus 12 is 8. Okay. And then, of course, my denominator is just going to end up being the square of that one. We'll have over 36. 8 over 36 I can reduce to 2/9. All right. Fy at 1, 2. Obviously, my denominator is going to be just like it was before. It'll be that 36 that we had. But now I'm going to have 3 minus 12 plus 3. So 6 minus 12 is -6. And then I've got -20 here, right? So double check. -12. Yep, plus 6. -6 minus 20 is -26. And of course, I can reduce that one at least by 2. So I'll have 13 over 18. Right? Okay. Okay, so I've got my derivative pieces, which means my normal vector at that point is going to be the vector 2/9, -13/18, and -1. Right? Got my normal vector. Let's create the tangent plane and the normal line now. So my tangent plane is going to be the 2/9 times x minus 1 minus 13/18 times y minus 2 minus z minus 11 over 6 equals 0. And of course, it's completely fine to leave in this format, right? Depending on what you need. Other particular things like might be, oh, well, I'd rather have the z by itself. Good news about most of these is it's easy to get z by itself here. All I would have to do is simply distribute the negative here and add the z over, right? So if I did that, what I would end up with is plus 11 over 6 is equal to z there. Because I would distribute the negative, and the minus 11/6 would become plus, the z would be negative, and then I'd add it to both sides. So it's just as easy to have the tangent plane, right? Like this. If I were going to have to write it in the other general form where you'd have number x, number y, number z, I would definitely want to multiply by some things here to get rid of a lot of these denominators. Like probably we would multiply by 18. That would be the best thing to do. And then I would do a lot of distributing and regrouping of the numbers, but that's just plain arithmetic at this point. So I've got my tangent plane to that point now on that surface. Okay. Now the normal line. Let's see, we'll call it L, I guess. Okay, x equals, I've got 2/9 times t plus 1. Y is negative 13/18 t plus 2. And then z is going to be negative t plus 11/6. This will be your normal line. Okay? So really, you can tell most of the work to finding a tangent plane or a normal line is going to be done once you've done all of the partial derivative portions, right? So I've got not much left to do after I've done these partial derivatives. You just got to make sure and plug in everything right and have all of the numbers ready to set up in your normal vector. Okay, let's work on the next example now. X cubed minus 2xy, right, at the point negative 2, 3. Let's go ahead and get our z value. G of negative 2, 3 is going to be equal to, I've got negative 8 minus 2 times negative 2 times 3. So that's 4 times 3 is 12, minus 8 is 4. Okay, so I've got my z value now. Let's get our partial derivatives. G sub x is equal to 3x, right, squared. And then I've got minus 2y right here, right? Okay. And then gy, the partial derivative with respect to y, I've got 0 for this one, and then I've got minus 2x. Great. So then my values of each of those, right? Let's go ahead and do the vector values. Gx of negative 2, 3 is going to be equal to, I've got 12, because that's 3 times 4, minus 6, so 6. And gy at negative 2, 3. Of course, the y value doesn't matter here. It's just going to be 4. It's negative 2 times negative 2. All right. So then my normal vector, in this case, is just going to be 6, 4, negative 1. Right? That was the formula for the normal vector, right? The partial derivative of x, partial derivative of y, and the negative 1. So then my tangent plane at P is just going to be 6 times x plus 2, right? Because it's minus 2, plus 4 times y minus 3 minus z minus 4 up there equals 0. Okay? And for my line, let's go ahead and put it in parametric vector form. I'll put it as a vector function this time. That would just be 6t minus 2, 4t plus 3, and negative t plus 4. Okay, so don't forget, parametric equations can be also listed as vector functions as long as you're using it appropriately. Okay? All right. Now the last one here, the last example I have, the p of xy equals e to the negative x squared minus y squared. This particular one is going to be useful if you ever do 3D probability functions, right? This particular one right here is the 3D extrapolation of a bell curve, basically. Okay, so what you can do is, talk about probabilities being the areas under certain regions, or the volumes under certain regions of this particular thing. However, it's not normalized yet, but you get the idea. Okay, So this particular one right here, again, same method. Let's go ahead and get our z value, and let's find our partial derivatives. So p of 0, 0 is 1, right? Because it's going to be e to the 0 minus, or 0 plus 0. E to the 0 is just 1. So I've got my z value here. And my partial derivatives with respect to x and y are, here, remember this is going to be a chain rule, so he is going to be his own derivative. I'm going to have the e to the negative x squared minus y squared in the derivative. And then the inside derivative, since it's an addition, I get just the piece that it's corresponding to. So I get negative 2x for that one. And the partial derivative with respect to y, not much different, except it's just negative 2y, e to the negative x squared minus y squared there. Okay, so then let's get our values of those two. So px evaluated at 0, 0 is just 0, and py at 0, 0 is 0. Okay? So notice what this amounts to is the gradient of p at this point would have been 0, 0. Okay? But the normal vector to the point is 0, 0, negative 1. Okay? So we've got our normal vector there. And notice that the normal vector is sticking directly down in the z direction there. It has no x or y component to the normal vector, right? So this is actually going to make a horizontal plane and a line, a normal line, which is parallel, where in this case, since it's at 0, 0, right on top of the z-axis, right? So for my tangent plane here, notice I have 0 times the x, so it's gone, 0 times the y, so it's gone, and I'm left with negative z minus 1 equals 0, or in other words, z equals 1, which should make sense to you, right? If I'm doing a tangent plane and we've come up with a normal vector that's completely in the up or down direction, that means I'm getting a horizontal, right? Because the vector's sticking straight up in the z direction. So what does that mean? It means my plane must be completely horizontal, or rather parallel to the xy plane, right? And it's at this z value of 1. So it's sitting right on top of probably a mountain, right, or a hill of some sort, and it's making the tangent plane horizontal. And then the normal line, right, is going to be the parametric equations, where x is just equal to his value of 0, y is equal to his value of 0, and z is negative t plus 1. Right? So then that's my normal line there. And this is my tangent plane at that point of this particular surface. This is all of the arithmetic that goes behind that. Well, not arithmetic, all of the calculations and the calculus and the theory that goes behind these surfaces. But let me show you what they look like graphically in GeoGebra. Go take a look at that right now. Here we are in GeoGebra. Let's start by looking at the first function, f. It has this cool looking swirl shape right here in the middle, but it really flattens out the further out you go. You see, you can zoom out really far and see
The rest of the function is pretty boring. The important parts are these two major hill features, one really high peak, one really low peak, around the center, close to the origin there. The upper top peak here is in this first octant where x, y, and z are positive. The point we were interested in is 1, 2, 11/6. It's that point right there on the surface. And we were constructing the tangent plane and the normal line there. So here is the generic tangent plane. And you can see it does only skirt the point. But since the plane is, of course, so generic and big, you can see it actually cuts into the function elsewhere. But don't forget, the part of the tangent plane that we're truly interested in is only the part that's really close to the point anyway. This is the tangent plane in its entirety, but we would much rather see this kind of thing like this. See how this is a circular cutout, well, elliptical cutout of the tangent plane there, centered at the point in question. And even the size that I've put here is too much. What we're really interested in here, and take away this, what we're really interested in here is if we were to decrease the radius here a bit. As you can see, it's still the tangent plane, quote unquote, but I'm really only looking at that small piece of it. Okay? It's still in the plane. Here, see? It's still in the plane, right? But I'm only interested in this smaller piece of it usually, especially when we're using this for approximation purposes. So I could even zoom in even closer here. I'm only interested in probably something even smaller than that. And you can see once you get close enough, it stops intersecting the surface as much and starts being truly just tangent next to it. You can't really see the separation still between the two, but you can see that it's there. That is the tangent plane, and that's the piece that we would typically use for approximations, rather than this bigger version right here that starts to intersect and go underneath. And you can see that that's what's happening. It's intersecting, and part of it's under the surface and part of it is over the surface there. Okay, and the normal line to F is this guy right here. As you can see, it's the line that is completely perpendicular to the tangent plane. All right. So let's bring that tangent plane back up here. Turn that surface off. Right? You can just take a look at how that's perpendicular to the whole plane there. And that's considered the normal line to the surface. All right, let's move on to the next function. We have function g, which is the x cubed minus 2xy surface. Has a cool looking saddle point there in the middle. It's not as straight of a saddle as some of the other ones, but as you can see, it does have that over-under, parabolic under, parabolic over, saddle-ish shape there. And the point that we were interested in G is -2, 3, 4, which ends up being way over here. And I can just zoom out a little bit to give it a better destination there. Okay, so then the tangent plane here is this one. And again, we're not as interested in the whole plane, because look, the plane intersects the graph in other places. You can actually see the plane going through other parts of the function. And we're really only wanting it to be just the tangent plane here at the point. So then I would probably be interested in it more like this. And you can see what I've done is I've made an ellipse cutout that's centered at the point in question. but it's still in the tangent plane. It's still the tangent plane there, right? If I increase the radial size, you can see it's still in the tangent plane there. So I can turn the tangent plane off, and that red circular or elliptical shape there is going to represent it. But again, we're only really interested in it when we're looking at a small portion of it that's close to the point. That's really going to be the part that we would use to approximate a function close to a point right there. And of course, you need higher techniques if you wanted to do a non-linear approximation. But this would be considered a linear approximation if you were going to use this tangent plane, not a larger version of it or anything like this. Okay, and the normal line, of course, is going to be perpendicular to that particular plane. As you can see, those are the equations that we wrote down right here. And it does give me the line that intersects that point and is completely perpendicular to the tangent plane. Alright, let's move on to function h. And as I was saying before, it's really something more interesting, like a bell curve, an extruded of a generic version of a bell curve, but it's really just close to the center there, because that's where a lot of your probability is going to be. Bell curve is all about centralizing the probability around a point. So I got this hill shape right close to the 0, 0 center there, and the rest of the graph is going to be mostly flat. It's not, of course, it's not completely flat. It can't be, but mostly up against the xy plane there. Okay, so the point of interest was when x and y were 0, 0. So as you can see, that's the point here at the top. To see a lot of this better, I'm just going to turn the axes off. So we're looking at this point on the top of the surface there. And the tangent plane would just be the z equals 1, which I've done circularly here. That's the tangent plane right there. Okay, and in this case, it really doesn't matter really how small I get this particular one, but we can try. Yeah, it's already set up to do it. Okay. So as you can see, no matter how small I get this particular plane, it's still going to be a little bit, you can see the separation there. And it's because it's at the top peak of that thing. Let's go down to 0.1, right? That's a really small version of that tangent plane. But this is the tangent plane. You can see it's horizontal. And it's horizontal because we picked the point that is actually the very top of the peak. Okay, so then the normal line to this guy here is this, which is actually the z-axis, but I turned the axes off so you can see it. But it is going completely vertical there, parallel on top of the z-axis.
Okay, I wanted to throw a couple of more examples at you just to have some other variety to go along with this, right? So I have an a function here is equal to 2 times sine y times cosine x. And basically the shape of this one is like an egg crate. If you've ever seen like a carton of eggs, you know, they have the little humps in between that the things fit into. It looks kind of like that because the sine y and the cosine x, remember sine and cosine are out of phase by 90 degrees, right? So if you make one dimension, you know, sines and one dimension cosines, they tend to make this ripply looking, even looking egg crate, yummy shape, okay? And the b function over here, 3x over y, is another interesting twisted shape. It's fun to do. Okay, so let's go ahead and do our tangent plane and normal line here. To do our tangent plane, first of all, remember we want our z value. So let's do that first. A of negative pi over 6 pi over 4 is going to be equal to, let's plug it in, I've got sine of pi over 4, which is square root of 2 over 2. And then I've got cosine of negative pi over 6. But then that puts it in the fourth quadrant for x, right? And cosine of a negative is going to be a positive anyway. Cosine of pi over 6 is cosine of 30. So that's square root of 3 over 2. Right? Okay. So then my z value is going to be square root of 6 over 2. Right? Got my z value. Let's get our partial derivatives. A sub x is then equal to the 2 and the sine y are along for the ride, right? They don't have anything x in them. And then it's times the derivative of the cosine x part, which is negative sine. So I'll just make some space here. So equals negative 2. And then I've got sine x like that. Alrighty. So then my partial with respect to y, same idea, right? The 2 and the cosine x are along for the ride. Derivative of sine y is cosine y. So I've got my derivative 2 cosine y cosine x. All right, let's find our values at the given locations, right? My partial derivative with respect to x at the negative pi over 6 pi over 4 location. Right here, I'll have negative 2 times sine of the pi over 4, again, still gives me square root of 2 over 2. And then the sine of the negative pi over 6 is going to give me a negative, right? Because sine in quadrant 4 is negative. And sine of pi over 6, sine of 30 is 1/2. So I'm ending up with a positive, right? Square root of 2 over 2 for that piece. Okay, so then my component in the y direction there, whoops, at the point negative pi over 6 pi over 4 is going to be equal to, I've got 2 cosine of y, square root of 2 over 2, and cosine of the negative pi over 6. That's still the square root of 3 over 2 there. Okay, so I'm ending up with something very similar to my function value, right? Square root of 6 over 2 there. Nice. All right, so then I need to put together my normal vector. Okay, my normal vector is going to be square root of 2 over 2, square root of 6 over 2, and negative 1. Okay, so mind you, by the way, if you're ever, just disheartened by seeing fractions and things like that in your vectors, don't forget, we didn't say that this had to be a unit vector, and we also didn't say that this had to be any particular size in general even. So if you wanted to, you could actually factor out the 1/2 and throw it away or whatever. All I really need is the direction from this. And if I were to multiply by a scalar here and say get the vector square root of 2, square root of 6, negative 2. These are going to be parallel vectors because they're only a scalar multiplication of 2 away from each other. And if that makes your day easier, then go for it, right? As long as the direction is preserved, then your plane and your line, your tangent plane and your normal line are going to be unaffected, okay? All right, so let's write down the official tangent plane normal line here. My tangent plane here at some point P is going to be equal to square root of 2 over 2 times x plus pi over 6. plus square root of 6 over 2 times y minus pi over 4, and then minus z minus square root of 6 over 2 is equal to 0. And then, of course, my line, my normal line, parametric equations, x equals square root of 2 over 2 times t minus pi over 6, y equals square root of 6 over 2 times t plus pi over 4, z equals negative t plus square root of 6 over 2. Okay? On my other example here, we'll just have the same process, right? Let's go ahead and jump right in. Find your z value. So that's b of 1, negative 3. And let's see, when I plug in 1, I get 3 times 1 over negative 3. I'm getting negative 1 for my z value. Next, let's get our partial derivatives here. So partial derivative with respect to x is going to be equal to just 3 over y. Because the derivative of the x, it's just multiplied by the constant 3 over y. Derivative of x is 1, right? Then my partial derivative with respect to y is the 3x is along for the ride, don't forget. Okay, so it's still there. And then the derivative of the over y, remember I would just make it y to the negative 1 and do a power rule, which would drop the negative 1 and give me a negative 2 power. So I'd have negative 3x over y squared. All right, so let's get our values here. The partial derivative of with respect to x at the location 1, negative 3 is solely based on y, right? So I just have 3 over negative 3, which is negative 1. And partial derivative with respect to y at the location 1, negative 3. I have negative 3 times 1 is negative 3 over 9, because negative 3 squared, right? So negative 3 over 9, which is negative 1/3, right? Got my two components here now. So my normal vector, remember whenever we're creating these normal vectors, it's not for always and for all normal vectors. It's just specifically the normal vector at this point, 1, negative 3, negative 1, right? That's the point on the surface, and this vector will be normal only at that point, perpendicular only at that point. Okay, so then I've got negative 1, negative 1/3, and of course the z is always negative 1 for my normal vector. And then we can create our tangent plane and normal line. Tangent plane at point P is going to be negative 1 times x minus 1 minus 1/3 times y plus 3, and then minus z plus 1 is equal to 0. And then my normal line, let's put this one in vector form just to be different than the other one, right? My x component of the normal line is going to be negative t plus 1. My y component is going to be negative 1/3 t minus 3, and then negative t minus 1 for the z component there. Let's look at these last two examples real quick. Here's the a of xy, 2 sine y times cosine x. And as you can see, it's just as I was describing. It's kind of like a carton of eggs.
egg crate looking stuff. They have the sines and the cosines that are out of phase with each other in the different dimensions, going left and right and in and out. So you can see the hills just alternate. Let's zoom in a bit, because the point that we are interested in is point A, negative pi over 6, pi over 4, square root of 6 over 2, which is located right here, close to the origin on the egg crate shapes. It's just on the back side of one of these hills from the first octant there. Zoom in and get a good bit more detail in one of these pieces. All right, so the tangent plane that we calculated was this guy right here. All right, and as you can see, it's very much tangent to this guy right there. And don't forget, what we're really interested in is just the piece of the tangent plane that's close. But we are actually on the tangent plane there. That's the important point. Then the normal line is this set of parametric equations, as we wrote already. And it gives us that line that is perpendicular to the tangent plane at that point. So as I zoom out, you can see the scope and the whole thing here. Okay, let's take a look at the other surface. Surface B, 3 times x over y. It's kind of like a plane that's been twisted. You can see the real twist there. Let me zoom out a good bit on this guy here, so you can get the feel for it. It has a weird saddle point that's more of a sideways saddle here, as you can see. The domain of this plane, as you can see, is not the whole entire xy plane. It does have these regions cut out there, and that's just because of the way the division of the y is working, right? Whenever y is 0, we have a bad piece there, so we don't want y to ever be 0. And really what's happening is that that part is not cut out of the domain. The more of the graph that I'm able to zoom out on, you can see the triangular regions get smaller. The only true thing that's cut out of the domain here is going to be the points where y is 0. And you're getting sort of a vertical asymptote feature there. Alright, so then where's the point that we're interested in? Point B was 1, negative 3, negative 1. Here it is located over here. And I actually have the xy plane turned off. As you can see, this would be the xy plane. And the point is below it. The z value is negative. So I have the plane off so that we can see a little bit better. Okay, so here's the normal view right here. The first octant is looking at us with the positive y, positive x, positive z. I have to go over to this other octant behind and below over here for this point. And here's the tangent plane. Because of the way the function is curved, the way the surface is curved, the plane alternates, above and below. You can see these two pieces are above, and then these two pieces right here are below the surface down here. But it's tangent at this one point. And like I was saying in the last examples, remember, we're only really interested usually in a tangent plane locally right there. And then of course we also have the normal line going through the surface there. And it is perpendicular to the tangent plane.
Another little side note to wrap up this particular lecture, we need to talk about the incline of a plane. And you've probably seen something like this before when you were discussing directional cosines, either in Calc 2 or Calc 3, when you first started looking at 3D vectors. The idea here being we can discuss sort of like a slope, but really we just do it with angles. Every once in a while you need to know how a plane is inclined. Therefore, what we do is we compare the normal vector to the z-axis, basically, because the normal vector controls the direction of your plane. So however it's canted off of the z-axis, remember in spherical coordinates, that angle would have been called phi, because it would be the angle coming off of the z-axis to whatever point you're talking about. Okay? And it works just like any other dot product. The directional cosine of something is just going to be your vector dotted with the direction that you're interested in. In this case, n dot the k direction, so that's the z unit vector, right? Divided by the length of n. Technically also divided by the length of k, but the length of k is 1. It's a unit vector. Okay? So we can find the incline of a plane this way. And then whenever we're talking about tangent planes, the incline becomes important, just so I can judge what direction that particular plane might be inclined on the surface, right? So of course, the example that we just went through, right? I found the equation of the tangent plane here. And then what I did beyond that in this one here is I just simplified it. I distributed all of the pieces, I combined all of the numbers, I got rid of the negatives, and I cleaned it up, right? So this is the actual general form equation of that particular tangent plane. And then if I wanted to compute the incline, I have the cosine of phi is, and notice I just have the 3, right? N dot k. Whenever you do that, it's just going to be the z component of n, basically. Okay, so 3 in this case. And then I'm dividing by the length of the vector 3, 1, 3. Now, notice that's not actually the original normal vector, and I even commented on this earlier. As long as it points in the right direction, we don't really care too much about the size of the vector when they're applied to these normal lines and tangent planes. Okay? Because look, I can set up and the length is there according to this vector, or I could also have set it up with the original normal vector here, in which case the absolute value of that dot product would give me 1. And then I would have 1. 1/3 squared is 1/9. -1 squared is also 1. If you add these up and get rid of the compound fraction, what you'll realize is you end up in this exact same spot. Either way, you're going to end up doing the inverse cosine of 3 over the square root of 19, and the angle between the z-axis and your plane is going to be 46.5 degrees. Sort of have the same incline, okay? So I hope this has helped you understand tangent planes and normal lines to surfaces.
Let's wrap it up by looking at the incline angle here. So as you can see, here's that same surface that we were talking about. There's the point in question. We had computed the tangent plane, right? And I have the little grid showing on it this time. The tangent plane is then the only thing that we're concerned with. And then we have the normal line here. But I'm not really concerned totally with the normal line. What I'm really interested in is the normal vector n. So I can take off the normal line and you can see the vector there is normal to the surface. I use the vector 3, 1, 3, which is actually a scalar multiple of what we originally calculated. We originally calculated the normal vector to be -1, -1/3, and -1. This 3, 1, 3 was just a scalar multiple of it, and it's in the same direction, just anti-parallel with it, in a little bit different size, that's all. So then the incline, remember, is going to be the angle of this normal vector with the z direction. So if I turn off the plane for a moment and turn on the k vector, you see there's the k vector at the point. The angle that we computed between these two was the 46.51. So what does that mean? When I've got the tangent plane here, the incline angle from the z-axis is this angle here. Notice if I were to actually compute the angle of the plane itself with the z-axis right here, it's not the same thing. You can see it's the 43.49, right? But also notice that if you line it up just right, the two angles add up to be 90 degrees, right? And you can see that in the numbers too. If you add these two together, you get the 90 degrees. That's actually between the normal vector and the plane. So my point is, just notice that it's not the angle necessarily between the plane and the z-axis. It is the angle between the normal vector and the z direction, like this. So that gives us the incline in sort of a more familiar tone as far as like our spherical coordinates and things like that. Okay?